Hello, and welcome to another online learning day for Science 9. Our essential question that we're going to focus on today as we continue to think more about what we know about the universe is how do we determine the distance to objects in space? So that is going to be our focus for today. Let's get started. Would you please set up your focus note page? You can see that our topic is distance to objects in space. Depending on when you're taking these notes, fill in whatever date it is. And then how do we determine the distance to objects in space? Again, is the essential question. So what we're going to focus on today is just another new piece of information. So based on what we can observe if on Earth from space, we can answer these kinds of questions. How do we determine the distance to objects in space? Okay, that gives us and reminder for this set of notes, you're looking for things in this color. So if things are in this color, that means you should write it down. Everything else is just things I want to talk about and part of our lecture, not necessarily notes. Okay, so let's do a quick thinking about where we finished last time and where we're going today. So there are four things that we as scientists feel we can learn from space from studying waves: the distance to an object, the temperature of an object, the elements that make up an object, and the speed of an object. And again, I don't know why I put them in this order because we've already done number 2 and 3. Temperature of an object. Remember the wavelength that comes like from the sun. We can measure that. There's a math equation. We can figure out the temperature. Elements that make up an object, we can measure those things called spectral lines from what we appear in space compared to what we appear in a lab situation here on Earth. We can compare them and we can actually just match spectral lines to determine the composition of an object. And then we're going to talk about speed of an object tomorrow. Today, though, the distance to an object in space. That's where we're going. Okay. Do this for me real quick. Try this test. So right now, wherever you are, set down your pen, pencil, or your iPad, or whatever you're doing, and close one eye. Doesn't matter which one. Stretch out your arm in front of you, and I'm doing this too right now, even though you can't see me. Hold up your thumb and look at your thumb with your open eye. Okay, so kind of remember where it is. So make a mental note of where your thumb is when you look against the background. So maybe it's your wall or whatever is in front of you right now, way past your thumb. Okay, now close that eye and open the other eye and observe your thumb. Do you notice that it seems like your thumb is moving? Like mine looks like it's in a totally different arm, like a totally different person. And you can even go back and forth, leave your thumb in front of you and go back and forth, open, close, like left eye, right eye, open, close. So that what you just noticed is something called parallax. Boom, drop the mic. You just got learned. Something super simple, opening and closing your eye, shows you something that is a real scientific phenomena called parallax. And that is our big new vocab word for today. Okay, stop playing with the parallax idea, the open and closing of your thumb. I know it's amazing, but we got to keep going. All right, so here is the definition of parallax. Parallax is the apparent shift of a position. Because notice when you were holding your thumb out, you weren't actually moving your thumb at all, your arm at all. But it's the apparent shift of a position of an object relative to a background when the observer of the object changes position. So again, the object is not actually changing position. In our case, with the two different eyes, that's how we changed position, because one eye is on one side of your face and the other eye is on the other side of your face. Here's another kind of visual. So like viewpoint A, when you looked at this object, you can see it kind of looks like a star, because that's where we're going with this. It looks like the object is over here. When you view from the second place, you view the object, it looks like it's over here. So when the observer changes position, it looks like the object actually moved. And so showing you that when you stood at A, it looked like the object was here. When you stood at B, it looked like the object was here. So that shift, that distance between where you were standing and where it looked, and then you change positions and where it looked, that all of that can be measured, and that can give us an idea of where that object is actually located. So it's not just an interesting topic. We actually measure how far it looks like it shifts, and we apply that to measuring the relative distance of stars. So when we stand here and we mark where it is, and then we stand here and we mark where it is, measuring that distance between those two, like how far it seemed to have shifted, we can use some geometry, some angles, some things like that, and we can actually identify how far away. So, because of how much it appeared to move, that tells us how far away the object is. So, there's some geometry and stuff that has to happen. And we're not going to get into like all of that, but I'm just asking you to trust me based on math and science, the measurements and the geometry, we can identify where that object is. So that's kind of the background or the introduction, I guess, sort of parallax. So back in the day, ancient astronomers, so people that were, and we're talking like hundreds and hundreds of years ago, when they were to look out into space, they were pretty convinced that the Earth didn't move. We don't fly off or fall off the Earth when we jump. So like if we jump up, we come back in the same spot. So that must mean the Earth wasn't moving. They were looking at stars and it didn't seem like the stars had any parallax. And they never considered the fact that, well, the reason that when you just look at the star with just your bare eyes, the stars are so far away that we don't necessarily notice it. So for example, let's do that thumb trick again. If you put that your thumb right by your nose and go open, close your two different eyes. Okay, now stretch out your thumb as far as it goes and go open, close, open, close. Notice that when the object was really close to you, there's a lot more parallax. So the farther away an object gets, the less parallax we notice. So when we were trying to figure out how far away stars are, we need to have something really good to look at them. So advances in technology were how we figured out, you know what, we can see parallax of planets and stars and things like that, because the objects were just so far away. So that was just kind of a little back history lesson. So Tycho Brahe was one of the first people that at least recorded parallax. Now it's very possible there were ancient people way before that in different countries, different people that noticed it. But he was the first one to record it and use this idea of parallax with a distance to a comet. And then our technology now, like especially telescopes, has gotten so much better. But parallax is still the only experimental way to measure the distance of objects outside our solar system when they're that far away. So the point is that even though we have really good telescopes now, they still can't measure how far away distant galaxies and stars are, because they're just so far away. So that's kind of an interesting thing too, that even though our technology is so much better, we don't have some type of measuring system that can, telescope out into the space, the depths of the universe. We still have to use parallax. So that really simple thing you just did with your eyes and your thumb, that is still being used in the advances of technology today. So here's kind of the conclusion. So advances in technology allow us to see parallax of stars. And then again, we use geometry to actually determine the distance. So once again, so at one point in the year, we would observe a certain star and we would see where it is. Then we got other background stars that kind of help us give that reference point. And then at some point, our Earth is during a year, our Earth is in a different spot around the sun. And you can measure how far away you moved. So the observer is moving, observe the star again, and again it's all these different like angles, right? So you create these different triangles and measure the angle from here, and then how far away did it seem to move or shift, all those different pieces. So that's the part that for now I'm just going to ask you to know that it is based on math and science. If you take our astronomy class here at Roseville High School, like next year or the year after or something, you can get more into how they use the geometry. For now, we're just going to take advantage of the geometry that's been measured and then get to the part where we can figure out the distance of stars. So again, here's kind of the idea. So in July, you measure a certain star. You have that certain straight on from the sun. It should be right there. And then how far did you move? So from where you are to here, and then observe where the star is. And then you can do the same thing at a different point. So you can figure out that angle, right? So because you know this angle of how far you moved, and then you can figure out, oh, because I moved this far and I moved at that angle, you can figure out this distance. So again, that would be sort of your geometry skills that would figure that out. And that's it. That brings us to the end of today. So after that introduction, we can figure out how far away objects are in space. So here's your to-do list. Notice that obviously I didn't have you do any Costa questions during our notes because it was so short. So go back and do your Costa questions. Go back and do your summary for today. Think about, can you summarize what you just learned? because that is a huge deal. Oh, and your answer shouldn't just be parallax. So the answer to the question, how do we determine the distance to objects in space? Not a one-word answer. Don't just say parallax. I do have an assignment for you to work on that practices predicting how far away galaxies are. It's graph reading skills. So here's a chance to kind of practice seeing a graph that's already made and kind of seeing like what makes it a good graph, because you're going to be making a graph later in this unit for like a scientific graph. And then again, the purpose of this assignment is to use parallax shift to determine the distance of different galaxies. Just a reminder, if you have questions on this stuff or other past stuff that should have been turned in, remember I have office hours every day at 1:30. You just have to let me know you want to come to them, and then I open our Zoom so that we can chat. And then speaking of Zoom, so the next time, it feels like it's been a long time since I've seen you. Our next Zoom will be tomorrow if you're watching this on Wednesday. Tomorrow, Thursday at 9 a.m. will be our next Zoom as we continue to Unit 2, Day 4. Have a great day. Thanks for listening. Bye.